Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will implement Hausdorff distance, a very important metric in semantic segmentation and object detection. So here I'm looking at the Wikipedia page for Hausdorff distance, and it says this the Hausdorff distance is the longest distance you can be forced to travel by an adversary who chooses a point in one of the two sets, from where you then must travel to the other set. In other words, it is the greatest of all the distances from a point in one set to the closest point in the other set. So that was one definition of Hausdorff, and another way these distance can be expressed is the line right here, that it measures how far two subsets of a metric space are from each other. So basically the Hausdorff distance is the maximum of all the minimum distance between two curves. Let's see what I mean. So I have here, for example, two curves, and the red one and the blue one, and first I need to calculate the minimum distance between the closest point between these two curves, and then I take the maximum of all the minimum distance between these two curves. That's Hausdorff distance. So it's this Hausdorff distance is the greatest of all the distances from a point in one set to the closest point in the other set. So for an intuitive understanding why we need this Hausdorff distance at all, I found this beautiful blog right here. The link is cgm.cs.mcgil.ca. I'll probably give this link in the description. So what they are basically saying is that, let's quickly go through the blog. One second. Yeah. So the definition of distance between polygons can become quite unsatisfactory for some applications. Let's see an example, figure 1. So take a note of this figure right here, two triangles. The shortest distance here, the problem here is that shortened distance does not consider the whole shape. And why is that so? Let's quickly read through this block. We could say that the triangles are close to each other considering their shortest distance, which is this distance shown by the red vertices. However, we would naturally expect that a small distance between these polygons means that no point of one polygon is far from the other polygon. In this sense, the two polygons shown in this figure are not so close really, as their farthest point shown in blue, that is this point and this point, could actually be very, very far away from the other polygon. Clearly, the shortest distance is totally independent of each polygonal shape. So that's one problem with calculating the shortest distance between two shapes. Let's take another example, this one, another example given in this figure 2, and here the problem is the shortest distance doesn't account for the position of the object. So what they're saying is, where in this figure we have same two triangles at the same shortest distance than in figure 1, but in different position. It's quite obvious that the shortest distance concept carries very low informative content, as the distance value did not change from the previous case, while something did change with the objects, that is their position indeed. So these are the problem with calculating the shortest distance between two shapes. So, and this problem is more or less solved by the special distance called Hausdorff distance, which is the greatest of all the distances from a point in one set to the closest point in the other set. And the blog also gives a little pseudocode. You can go through this pseudocode to get the understanding of Hausdorff distance. Alright, so that was some theory behind Hausdorff, but now I'm going to implement it, rather use some packages to actually find Hausdorff distance between multiple tensors. And so PyTorch or TensorFlow doesn't have Hausdorff right inside it built in, but there are quite a few packages, and one of the very popular one is this one right here that I'm looking at, called Hausdorff. And yeah, so they have 182 stars, and last updated in 11 months ago. So yeah, this is one of the popular ones. So I am going to take few examples from these GitHub repo itself. They have given a couple of examples to implement it. I'm just going to follow that directly. So the first you have to, of course, install this package by doing pip install Hausdorff, and then let's do some coding here. SNP. I also need that. I have already installed that in my machine. From Hausdorff, import Hausdorff. All right, and now I just need to create two arrays from following the repos example, which is this. So I'm just creating first with a np.random.seed0, and then x and y are my two tensors of this shape, that is 1000 by 100. The column must match between them. That is, the second dimension must match between them. Let's run it. Yeah, obviously I got 1000 by 100 and 5000 by 100. And now I am going to print few things, again following their repo as it is. So here, test computation of Hausdorff distance with different base distances. So for the distance in this package, for this distance argument, you can give different distances: Manhattan, Euclidean, Chebyshev, and cosine. And also we can give custom distances according to your requirement. We will see the example right now, but first let's run this cell. Wow, they just calculated the Hausdorff distance for x and y, and keeping all these different distances. So the first one is Manhattan distance, Hausdorff, and the second one is based off Euclidean, third one is Chebyshev, and the fourth one is cosine. And now I am going to do a custom implementation of Hausdorff, and again following their repos instruction exactly. So that's my custom implementation. First, oops, sorry, this is not a custom distance, because this is still using the predefined Haber-Shine distance. So let's just delete it. Instead, my custom distance will be this one. So here I am first I'm importing number, because this is just-in-time compiler for Python that works based on code that uses NumPy arrays and functions and loops. And the most common way to use number is through its collection of decorators that can be applied to your function to instruct number to compile them. So this at number.jit, this is the most common way of using decorators with number. And then I'm defining a custom distance function. It's pretty much an Euclidean function. So this is I have two array x, array y, and then what I'm doing is for I in range n, and n is my the shape 0, and for I in range a, I'm just calculating the Euclidean distance by squaring array xi minus array yi, and returning this whole expression square root. All right, and now to use my Hausdorff distance, all I have to do is, one second, all I have to do is include this another print statement here where I am using the distance, these custom distance method. And then obviously I'm passing x and y that has already been defined at the top. That is this one. So let's run this. Awesome. So that's my custom distance functions implementation of Hausdorff. Now we can do many more crazy custom function implementation. Their official repo suggest another one, which is this. So here again, my custom distance function is much more kind of crazy. So what I'm doing is array xi minus array yi, taking cube of that, dividing this whole expression again by array xi square plus array y I square plus 0.1. It's pretty kind of very unique one for calculating the distance between array x and array y. And then again, I'm just bringing in Hausdorff distance, and to the distance argument I'm passing these custom distance method. Let's run it. Yep, I got my Hausdorff custom crazy test output as this. So those were implementation with that package. That is this one, Hausdorff. But now I'm going to calculate Hausdorff using Scipy and MONAI. You must be knowing both of them. It's two of the most popular packages in this world of machine learning and data science. So let's bring in some the standard modules from Scipy and MONAI. So from scipy.spa spatial, I need to bring in okay, I need to do distance here and import directed. That was Hausdorff, yeah. And I also need to do the same need to bring in Hausdorff from MONAI. I really just suggest you go through their documentation, because their documentation really explains well. I have to bring in matrix.utils, and from there import get mask ages, this one, and also get surface, I think this one, get surface mask, get surface distance, it should be FSCE DIS. Yep, this one. So with these two modules or these two methods of MONAI, I will calculate the Hausdorff distance. So first let's do it for the Scipy one. Calculate. It's a difficult word to spell. Hausdorff, D-O-R-F-F. Yep. And I need to pass in two tensor to it. My two tensors would be my prediction tensor, that is a predicted output values from my model, and the ground truth. So let's give pred gt and then max distance. And if np.all, obviously if all pred are equal to gt, the ground truth, then I just need to return the distance as 0, because in that case there is no distance between them. They are just in a perfect world. Predictions will be the same as ground truth. Return 0.0. I have to return float. That's what I'm doing, 0.0. And otherwise calculate the distance between them, which will be my directed Hausdorff. And with that I will pass my np dot. I need to bring in all the I need to find the indices of the array elements that are non-zero. So I'm going to do arg_where here. To that I will pass spread. Similarly, np.arg_where gt, and I don't need max distance yet here. Rather, I need to get the 0th element from this here. So distance will be directed Hausdorff np.arg_where prediction. Okay. And if least greater than max best, then so when gt ground truth are all 0, this may get to infinity. So if dist, sorry, it will be dist max distance, then it will be return 1.0, and otherwise return dist by max dist. And if you are thinking that why I had to bring in this 0, that is why I had to take the 0th element from the output of directed Hausdorff, it's pretty much as following their documentation. So this is official documentation of the directed Hausdorff in scipy.spatial, and this actually computes the directed Hausdorff distance between two 2D arrays. And what they are doing is similar, that is they have two tensor u and v, and they are calculating the directed Hausdorff on them and taking the 0th element from them. And that's because in the return value, that is what this method returns are these things. That is the first one is it's a double value, which is a directed Hausdorff distance between array u and v. Then it returns the second thing, which is index of point contributing to Hausdorff pair in u, and then third one is index of point contributing to Hausdorff pair in v. So you obviously, when you want the actual scalar value of the Hausdorff distance, then you obviously need to take the first element from the return array. And this max distance argument is something that we have to separately provide. So now I'm going to do the same calculation of Hausdorff based from the package MONAI. So let's define another function. Let me position it. Calculate Hausdorff, which is yes. PORFF. Actually, this one should be named as Scipy. SCIPY. Yep. It's a USDORFF under MONAI. And this also take red and GT and max DIST. So here, if np.all PRED equal to GT, then return 0.0, else. Now here is where I need I have to implement this method that we brought in from the MONAI package, which is get surface distance. To that I will pass first I want to make use of get mask edges, and that to that I'll pass spread and GT. And actually, if you go to the official documentation of MONAI and read their get mask edges, this is what they mention. This method do binary erosion and use XOR for input to get the edges. This function is helpful to further calculate metrics such as average surface distance and Hausdorff distance. The input image can be binary or labelified images. All right. So yeah. So from the get mask edges, I first get the what do I get? I first get the ages predicted and ages ground truth. That's what the get mask ages returns me. Return type tuple ND array both are will be ND array. All right, let's get back to our VS Code. Yeah, get mask ages. To that I pass GTN. Okay, and this will return me a tuple, so they will be my ages spread and ages GT. Oops, sorry. Ages GT. All right, and now, well, yep. And now I have to make use of these two return values and apply them on get surface distance to get my surface distance. So surface, yeah, this distance. Oops, why? Yes, ISTA. Surface distance equal to get surface distance. To that I pass ages spread and ages GT, and also the most importantly the distance metric. And once again it can take various distance metric, and in this case I'm going to pass Euclidean. What are the documentation saying? That we can pass Euclidean, chessboard, taxi cab. Yeah, so I'm going to take Euclidean one. CLIDEAN. All right, and now if surface distance is equal to 0 comma, then I'm going to return 0, else I have to calculate the distance as. So this distance is pretty much my Hausdorff distance. That will be equal to surface distance. I have to take the max, of this. And then just like this function, I'm going to do this little thing as my final return value. If distance greater than max distance, then return 1.0, else return, oops, I'm always misspelling, return distance divided by max distance. Okay, now I'm going to create a random tensor shape which I'm defining to be 128 by 128, and also I'm going to define my max distance by giving a custom function. So my custom definition of max distance will be equal to np dot square root, and to that I'll pass random tensor shape, take the 0th element, and then just cube it to the power of 3. To that I will add random tensor shape 1 and cube it as well. Am I doing it right? There is something, yep, this will come inside this. Yeah, so np dot square root random tensor shape 0 to the power cube plus random tensor shape 1 to the power of 3, and taking this whole expression, it is being square rooted by np dot square root. And now my grade will be np dot random np dot random random dot rand int, and to that I will pass the starting position remains 0, and for the high I will pass gh equal to 2. Size will need to match my random tensor, or random tensor shape. And similarly, I need to do for another vector, which will be my ground truth vector. So just I'm copying it down below and naming it GT vector. Otherwise, it remains same, np.random.randint 0 height equal to 2 size sham. Yep. Just print their shape to check that they are what they should be. Print. Actually, I can print. Let me see 1 second. GT vector. Okay, just do it. GT vector dot shape. Yeah, obviously. Okay, so now I can, and let me just print my final calculation. That is the final Hausdorff distance calculated from those two functions that we defined. So first one is Hausdorff Scipy. Oops, I'm again pressing enter, which is, I should press just tab. Calculate Hausdorff Scipy. To that I pass my pred vector and also my ground truth GT vector and max distance. Similarly, I do print calculate calculate. Why that's not coming? Calculate MONAI. Oops, sorry. HAUS MONAI. To that I pass pred, then GT vector and max distance. And now if I print, that should give me name Hausdorff Scipy is not defined. So what did I define? Oh, I never ran this cell. Yep. The truth value of an array with more than one element is ambiguous. So let me debug this. The error is coming from here. If surface distance equal to 0. Oh, so I think I got it, because I'm comparing a whole tensor with just a tuple. So it must be some form of shape. Let me see. This is the line. If surface distance, yeah, obviously. So I did not ever take the shape. I cannot compare. So the surface distance will be a whole tensor. I cannot compare that with only a tuple. I need to get the shape. This HAPE. And then it should be all right. So let me run it again from here. All the code cells below. Yep. So now it ran well, and I got the Hausdorff Scipy this value, and I got the Hausdorff under MONAI this value, and both are exactly same. And so the next thing I'm going to do between to compare the efficiency of executing the same code under Scipy and under MONAI, and check which one runs faster. So the classic way to check efficiency I will use is with the time module. So import time, then start equal to time dot time for I in range 100. Calculate calculate under Scipy. Let's give it pred then ground truth GT vector and max distance. And here is CIPY. Scipy, time taken under Scipy, time under, just name it Scipy time is CIPY, Scipy time equal to time dot time minus strt, and print just print this time itself, scipy, scipy time. All right, I got 2.8322, and now let's do the same for my MONAI. So okay, I need to get the start running. strt start equal to time dot time for I in range 100. Calculate under MONAI, spread GT vector and max distance, and then my MONAI time will be time dot time minus s start, and print MONAI time. And look at this, I got such a smaller value for executing the same code under MONAI. So let's just quickly check the ratio between them, that is how much more the MONAI time is faster compared to the execution time of Scipy. So just do MONAI, MONAI time divided by, sorry, it would be, because the Scipy time is much larger, so it would be SCI Scipy time divided by MONAI time. Yep, so my MONAI time is almost 14 times faster. That is, the Scipy time took almost 14 times more to execute the same code. So that was all about calculating Hausdorff distance using the built-in methods of various packages. And now I'm going to do a very simple from scratch implementation of Hausdorff distance with PyTorch. So yeah, let's import torch first and then define my Hausdorff torch function. Def s also DORFF 2D, and let's name it torch because I'm going to use torch xy. It will take two vectors xy, make x and y float, so x equal to x dot equal to t. Similarly, y equal to y equal to y dot float. Now calculate a distance tensor between them. A distance tensor will be, I'm going to use torch.cdist, which is a metric for calculating distance between two tensor in torch. So torch.cdist, and to that I need to pass x, y, and a p-value. P-value actually is a metric for which kind of distance that I am trying to calculate. So right here we can see the documentation, and for the p-value, p-value for the norm, for the p-norm distance to calculate between each vector pair. So when I pass p equal to 2, that means it will be squared, that is it is a Euclidean distance. And if you're interested, you can just quickly check their official documentation. It says computes batched the p-norm distance between each pair of the two collections of row vectors. And what are my row vectors? x1 and x2. So x1 input tensor of shape b by p by m, and x2 is input tensor of shape b by r by m, and p-value is the p-norm distance to calculate between each vector pair. All right, so cdist, and then I so from this I will get a distance tensor And now let's quickly check. Um, actually, I need to get the minimum value of this tensor. So value 1 will be equal to distance tensor along the axis of 2, because if I print this distance tensor, let me quickly show. If I print a distance tensor mean 2, sorry, actually let me print the whole distance tensor, then it will be more clear. But let me write the function first. Distance tensor, then along the axis, take the mean along the axis of 2. This will return both tensor and indices, and that's the reason I need to also take the 0th element from this, and then I have to apply max, and along the axis of 1, and I will, sorry, not 11, that's 1, keep dim, I will keep the keep dim equal to true, and I need to take the 0th element. So remember, originally I said that the Hausdorff distance is defined as a maximum of all the minimum distance between two curves. So in other words, the Hausdorff distance is the greatest of all the distances from a point in one set to the closest point in the other set. Similarly, I need value 1, value 2, value 2, which will be again just similarly distance tensor mean 1. This will be along the axis of 1, and 0 max keep dim will be true, TRUE, and take the 0th element. Now final value will be the concatenation of them, torch.cat. I have to pass a tuple of value 1 and value 2, and the final return value is just the max of this, RETURN equal to what I'm writing, value dot max along the axis of 1 and 0. All right, now let's create two random tensor. Let's do A equal to torch dot random rand n, and I will pass the shape of the random tensor that I will create 2, 3, 4. And also I create another tensor B, which will be torch. Actually, it will be just the same, and 2, 3, and 4. So if we print, let's print A and print B as well. Oh, I did not run the cell. Yeah. Yeah, so these are my two randomly created tensor, and I am going to apply the Hausdorff method that I just defined here on these two tensor. So print HAUS DOR distance says HAUS Hausdorff HAUS DORFF underscore 2D torch. To that I pass A and B. That's all. And that is my output from that. But looks like I made a mistake, because these final tensor should have just 2 elements. So why I'm getting 4 elements, let me quickly debug. So this is my value 1, value 2, which is applying the mean and then taking the max, and then I'm concatenating these two values. Oh, I did not mention the dimension across which it should be concatenated, and the dimension should be equal to 1. And that's why I think I got final 4 elements in the final output. So let's run it again. Yep, now it looks awesome. So I got just 2 elements in the final tensor, and this is my Hausdorff distance between these two random tensor that I created. And an obvious question may come to your mind, that why I got these 2 elements and not a single scalar value as my Hausdorff distance. That's because here the way that I have defined this method, it will take as its input of the shape batch, height, width, and there is no channel. So in these 2 input tensor that I have passed to my Hausdorff 2D torch, the first dimension is batch, then height, then width, and the output as well, the dimension of the output will be the batch, because I have 2 as a number of batches, and that's why I'm getting these 2 elements in the final output. So actually this is one Hausdorff distance and this is another Hausdorff distance. Both are individually scalar value, but the function will return me both together because the output dimension would be the batch dimension. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and Tensorflow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.